Miss Jody here on another video for Energy and Matter, or Matter and Energy class that usually meets on Thursdays from 9:30 to noon. We have this video plus one more that I'll be doing on current electricity, and then we will just finish. We'll have that be the end of our year so that this doesn't drag on too long. So these last couple chapters, I'm just trying to simplify a little bit so that we could just get a few things into our, or a few notes for our journals and understand a few of these fun concepts. And I was hoping still to get back together to do a couple experiments, like some of the experiments with magnetism. I'd love to do some of those. Those are fun. But if we're not able to, then some of the experiments I sent you via video, you can do some of those at home. And of course, always send me pictures. A few of you have sent me some pictures and I've loved them, and I printed them out actually today to get in the journals. So we would have some good pictures for this time that we've been separated. So just trying to finish up the journals, and hopefully, like I said, they'll give us some day when we're allowed to get together again, even briefly, and we can hopefully, if not, I'll set the journals out for everyone to pick them up, and we'll just have to do that if they don't let us. Well, this chapter being on magnetism, we saw last chapter was on electrostatics, and it's interesting how they'll teach on electrostatics, so the static electricity side of things, then they teach on magnetism, and then they go back to electricity, which will be the current electricity, and there's a purpose in that, because what they'll realize over time when they first started understanding static electricity, that was actually at the same time when they were starting to figure out magnetism too. It goes back to that same time period, just at different places. And but then eventually they find out that electricity and static electricity and magnetism are united, and that you can create electricity with magnetism, and magnetism, you can create magnetism with electricity. So it's pretty cool that they are now in our day and age united, but it's good to study them separate so that you get a feel for both areas, and then you put them together in the united life of electromagnetism. Okay, so magnetism, just pulled away from electricity. Let's just see what that means. So it's a property of attracting objects by magnetic force. So that means if someone says you have the property of magnetism, that's a property that it means you have the ability to attract objects using this magnetic force, or repel, of course. So this goes all the way back to 2,500 years ago, so back in those same time periods with the static electricity, when they started figuring out that there were certain substances, these natural substances in the earth that had this property of magnetism. And they had, back in the day, they had found a magnetic iron ore. So an iron ore is kind of like a rock that's filled with precious metals, and so they found some rocks that had these precious metals in them that had the ability to pull at a distance with this property of magnetism, or repel at a distance. And this magnetic ore, this big magnetic ore, was found in a province in Turkey named Magnesia, and that's actually how the magnet got its name, magnetite, the substance that was able to have these strange properties. So magnetite eventually became known as lodestone. So you've heard that before, of lodestone being a natural magnetic rock because it has the metals in it. And when they were starting to work with magnetism and starting to understand this cool property with the magnetite or the lodestone, they started realizing that the forces were concentrated in two main regions. So the two regions were, and they were opposite of each other. They were like on like two ends. And so that's why they became known as poles. So they called the North and the South Pole. And so the force being at two separate ends instead of just all throughout in random places. And they started realizing, just like with the static electricity, there was sort of rules that governed it. One is, unlike poles attract each other, just like the static electricity. If you have a positive and a negative, they attract each other, right? Same thing with magnetism. You have a north and a south, they attract each other. So again, was starting to see some similarities between the electricity world and the magnetism world, but at this time they didn't know they were of the same force, just two sides to the coin. And so they said, oh, hey, kind of like the static side of things, we have unlike charges will attract each other, and like charges will repel each other, just like in static electricity. Two positives together will repel, or two negatives together will repel. Same thing with the magnetism. Two north poles will repel, or two south poles will repel. And so it was, wow, some of these similarities were coming about. But here's one thing that was specifically different. The north and south poles, with magnets, they realized that they always exist in pairs. And there was no way that they could figure out how to separate them. What that means is, if you think of the static electricity, you can separate a charge, an object to be charged in a sense where it might take on a positive charge. It doesn't have to have the positive and the negative at the same time. You can separate those charges. So some object can be positively charged, another object can be negatively charged. But when it came to magnetism, there was always the north and the south, and they existed. And in fact, if you had a magnet, let me grab one of my magnets here. If you had, like, say, one of these regular magnets that we use, and you broke it in half, which I've had that happen in my classroom, you can see right here, and you say, okay, I broke this in half. So if I have one pole on this end and one pole on this one, now that's in half, do I have just this pole, just the one-sided pole? Like I say, that's the north and this is the south. Do I have just the north? But the truth is, even when you break the magnet in half, you still have a full magnet. This magnet can still do its bidding with picking up the paper clip and having its magnetic abilities. And so when you see that, you're like, oh, okay, that's interesting. So it's like they always, doesn't matter how much you break the magnet, it still has the north and the south pole. And so they haven't been able to find what they call a monopole, which would be just one side of it, supposedly. And so with the magnetism, with having the north and the south pole always existing in pairs versus the static electricity only seeming as if us in static electricity, you could separate the positives or you could separate the negative and it could exist without. So that was one thing that was a little different about the two, but there was a lot of similarities. In fact, the formulas that were being used for static electricity in the sense of understanding the strength of the charges was the same formula that was eventually applied to magnetism, and it fit, because meaning that with static electricity, if you have two things that are coming together, two charges that are coming together, and I'm going to use my magnets as an example. If I have my two charges coming together, the strength of this power of this magnetism, whether it's going to repel or attract, is all about how close I get it. So the distance governs that. And so whenever you see the power of magnetism, let me see if I can get it gets not, the strength is not there when these guys are separated. And they saw that with electricity too. The farther you got the charges away, the traction wasn't as strong. The closer you got them together, then it was stronger. So there was like a relationship between how far apart something was and the strength of the charge. And then they found the same thing with the magnetism. So they're not able to pull each other, but if they get close enough, you see how that other magnet started pulling as I'm starting to move it towards it? It's because it's getting closer, and the closer it gets, the more powerful charge, pull it has on it. And then eventually it has the power to pull it. And so that was something they were seeing with static electricity that they were also seeing with magnetism. And so that's super cool. So this was the start of them starting to put those things together. Now with magnetism, we have what's called the magnetic field. So it's a region surrounding a magnet in which other objects are affected. And so whenever you want to look at the magnetic field, you can take some of these magnetic iron filling containers. And I purchased these for our classes, obviously, because of so many years of using the iron fillings that are not enclosed in something. And if you look at my magnets, you can always see there's always like little iron fillings stuck to them. That's because you're always supposed to do this experiment when you're messing with the magnet. You're supposed to take the iron fillings, you're supposed to take the magnet and put it underneath. I'm going to get a few magnets here to make it pretty strong there. And you're supposed to put it underneath, and then you're supposed to use a a paper plate or something like that so that the iron can't get to the magnet. Let me see if I can scoot this over a little bit. Whoa, hey you. Okay, and that way it doesn't stick to it, because when you start sprinkling this on, you can see, you see how it's starting to form in the area of, and since I have two magnets there, it kind of looks kind of, but you can see the power of it, right? Super cool. And then if I pull this off, it's really attracted to it, so it's not even going to let me pull it off very much. There we go. Let me just take one magnet and see what we got here. Put this iron shavings on there. Now I'd have to kind of redo it to get the right lines, but these lines are called the lines of flux, and as I move it around, you see how it can kind of move. So it's basically, this magnetic field is the area that is affected by the magnet. So if I put the magnet on there, this whole area is affected by it. And so we would call that the magnetic field, the field around the magnet that has been affected. Now, when you're just looking at the magnet by itself, you don't see the field because it's the invisible field, right? Oh, I can't get this guy to sit here. If I have this, because now I bought these so that all the magnets or the iron shavings don't get all over everything. But you see what I can do here with creating the effect. And then I can say, okay, is this side of it affected by it? And you see there's some over there, but if I shake everything over there and try to get, there's barely any. But then there might come a point when I get it close enough where it's all gonna be affected. And so the magnets, these are kind of fun to play with because you can do all sorts of fun thingies. And then you can check like the power of that particular magnet, even with, will it make an effect on one above it? It still will. It'll go through. It's still powerful enough. And depending on what type, we can see I've got a lot of movement here, but then I can look down at my bottom one. Let me shake my bottom one this way, so it's all the way at the end. And then use this and see if my bottom one pulls any of that one. Come on. Getting it? It's getting some of it. I can see it moving. Some of it moved a little bit of it. But what if I take a second one? Try to make it stronger here. Can I get it? Put a whole bunch of these guys on here. Whoa. Not really moving too much of it there. But, so the tools of the iron shavings, or the little boxes filled with the iron shavings, or any of that, you can use to see the magnetic field. So the region surrounding the magnet in which other objects are affected. Now when it comes to magnetism, we have the three main metals: iron, nickel, and cobalt. These are the three main metals that have the property of magnetism. Now, you will hear other things being magnetized, and that's because they will be what's called alloys of these three guys. So say steel. So steel is an alloy. So that means it's a mixture with other elements, but it actually has one of the three metals in it. And so we can have alloys that have the property of magnetism because they're affecting the actual metal that's in there that has the property of magnetism. Now, magnetism, how does it work? So the idea is the theory behind what we call the domain. So domain is a group of aligned atoms having a single magnetic field. So what that means, I tried to do a little drawing here, and this little drawing says, okay, I've got this little block of metal here, of iron, nickel, or cobalt. And this little block here, all of the little atoms, they have the positive in the middle, and then they have the negative flying around them, like we see in the model of the atoms. And so in this, we have a whole bunch of atoms, but they're not like their spin and their electrons flying around. They're not all aligned. And so this is kind of all jumbled. The metal's all jumbled. So with the jumbling, we're not going to have the property of magnetism for that particular metal because they're not aligned. However, if I take a magnet and or something, or even electricity can do this, and I force the atoms to line up so that they are all in an aligned manner, then this piece of metal can take on the property of magnetism. So we call this magnetizing a metal. So if we have like an iron, a piece of iron, so say for instance, it was hard to find a pair of my scissors, but I have a bunch of scissors. Obviously we have up here in the upstairs classroom. And with these scissors, a lot of times the students will already magnetize them. So it's hard for me to find some that aren't, but these scissors have the metal in it that have the property for magnetism. But if, oh, nope, these are already magnetized too. Well. See, sometimes, let me see if these are. I thought I grabbed a pair that was not already magnetized. Oh, nope, these are magnetized too. See what happens when you teach the kids to magnetize metal, then they're all magnetized. Let me see if one of the teacher's scissors, hopefully they're not. Yay, okay. So all the little kids' scissors are probably magnetized. But so if I have my metal in my scissors here, and I try to pick up the paper clip, this is the idea that the paper clip or the scissors, all of the atoms of the scissor are all jumbled up like this, okay? But if I take a magnet and I move it across the metal in a certain pattern, and I'll move my paper clip for a second here, but if I have my scissors here and say I want to magnetize this part of the metal, then I take my magnet, and what I'm doing is I'm moving it along, well, if that guy's going to let me, I'm going to move it along the metal and then take it away from it so that I don't jumble them the wrong way, and then move it across, take it away, and then move it across, take it away. And my goal is using the power of this magnet to pull the atoms of the metal all in alignment and create the domains, the aligned versions of the atoms so that they can take on the property of magnetism. So I don't want to go back and forth, because then I'm just jumbling them up. I want to try to make it straight and then go away from it and then make it straight. And after a while, let's see if I've done enough, then I should be able to have magnetism. So you see my scissors are now magnetized because I got them in line. Now let's see about this other guy that was near it, this blade, see if it's magnetized. Nope, because I didn't magnetize that side yet. So this guy is, and this is the other side that I didn't magnetize, and it still has some properties, but when I flipped it over and it was the one that I was really working hard, it really flew up there. So I really got this side, see how it's moving it so much? I really got that guy going. But this other one, the other side of the scissors, I don't have. Okay, so along with that, then I can also demagnetize it. So that's the magnetized side. So I can try to use and sometimes it's harder to demagnetize them, but moving these in different ways, trying to get the atoms to move in and not be inlined sometimes, but sometimes it's hard to get it to demagnetize once you've already aligned them. So let's see if I've had any success on this. Oh, nope, still. I'm just making it I'm still getting, this is a pretty powerful magnet here. So I'd have to keep working at this and jumbling these up to try to get it to not be in order. And then eventually, if it was not in order, then I would have my metal that is not magnetized. And so that's the theory and idea of the jumbled versus the aligned domains. And then along with the aligning of and creating magnetism, we also have the idea of electromagnetism. Now, electromagnetism is when we actually, instead of using a magnet to line them up, we take electricity and we force this lining up as electricity is flowing through a metal. And the thing with electromagnetism is it's not permanent. I should have wrote that. Temporary, I'll just put temp. It's not permanent because the moment you turn off the electricity, instead of them being all aligned here, they go back to jumbled. And so you didn't permanently magnetize it. So with electromagnetism, normally, and I should have showed this diagram when I was talking about the poles, because you see the south and north pole, and then this is the magnetic field. This would be the whole field, and these would be called the lines of flux. And so it's areas of where the direction of the pull is and the repulsion, because it kind of like goes in the circular manner where it always goes down to the south and back up and then back around on both sides. So I should have showed you that. But with this one, This is for learning about electromagnetism and then creating your own electromagnet. And probably many of you have done this before, where you take a nail, and with your nail, you're going to wrap some wire around it. When you wrap the wire around it, if you attach it to, if you attach your wire to a battery with a positive and negative, the electricity can flow through the wire. And let me get a highlighter and I'll point this out here, that the electricity would flow. And it's showing it flowing from the positive to the negative, but that's not really how it goes, because with the negative flow to the positive, but whatever. So we would see, oh, I see why they're doing that, but you would see the electricity here. So because you've attached it to the wire and you wrapped it around the iron nail, iron has the ability to be magnetized, and so, but you got to force its domains. And so you have to do something, either use a magnet to put it in line like I just did with the scissors, or run electricity through it. So when you run, not through it, I'm sorry, around it. So when you coil the metal with the wire, and then the wire has electricity running through it, it'll force all of the little domains to get in line during the time when the electricity is flowing around it, and it'll create magnetism. And so if you take your little paper clip and you try to pick up the paperclip with the end of the nail will be magnetized. And so you will have a magnetic, a temporary magnet and a magnetized nail. And then you undo the battery. If you undo the battery, then it loses the electricity that was forcing them to get in line. And so then the paperclip would drop. And so many scientists over the years work to create really cool and really powerful electromagnets. So now they have really awesome ones. Depending on how many coils you have, you can get them super strong, and you run electricity through it, and they can pick up cars and all sorts of things with these electromagnets. They pick up the car and then move it over to an area where they want to drop it, and then they just turn off the electricity and boom, it just drops down. And so there's really a lot of cool things with magnetism. And I'm going to send you a video that just gives us some cool engineering sides of magnetism that I think you'll like, and it will show you some things with the electromagnetic world and how we can create things using this temporary magnetism. Okay, so I'm going to send you experiment for this in case you have the materials and you want to do it at home, and then you can put your data from the video over here of how you do it. And this is for if you want to do the experiment with the iron shavings thing that I put out there, and you can put your data on that around there of what happened. You can do little simple experiments like we would have done this if we would have been together, something like this, where I make the magnetism bottles, where you take metal things, and you put it in the bottle, and then you use the magnets to, just like the iron shavings, to manipulate and create really cool things with the magnets and stuff. So you can do experiments that I'll send you some links to do, and you can give me any of that information on this little note sheet. And I just made it really simple lesson today because we're almost finished, and I'm going to do, so I just want to do these 2 pages and then one more lesson on current electricity, and then we'll be done. Okay? All right, so I hope you're doing well, and I do hope to see you again. Oh, I didn't want to forget this guy. I forgot about this little metal ball thing I love, where you can create, using magnetism, all these little magnetic balls, and this is the main magnet source down there. So things like that you can have some fun with. But I do hope to see you, and I'll be in touch if they allow us.